in Harvard University, where she completed PhD in 1991. And after that, she went for a couple of postdocs, one from Brookhaven National Laboratory and another from Friedrich Institute of the Max Planck Society in Berlin. Then in 1996, she joined the JNCSR as an assistant professor. Right now, she is there in theoretical science unit of Jawaharlal's JNCSR as a professor. She has many awards and honors in her name, and just count few that she received Kalpana Chawla Women Scientist Award from the government of Karnataka in 2010. Same year, she also conferred with Stri Shakti Samman Science Award. She has been recipient of MRSI medal. She also became Fellow of National Academy of Sciences in 2011. And one thing I got to know from many of the sources that she is strongly promoting the science culture among the women at the national and international level. And she is a member of the Standing Committee on the Women in Science of the Government of India, and was formerly a panel member of the Women in Science Initiative of the Indian Academy of Science. So with this, without any delay, I would like to invite her to deliver today's physics colloquium on using descriptors to design novel nanomaterials. So Professor Narasimhan, over to you.
Thank you. It's a real pleasure to give this talk. Can you see my slides? Hello?
Yes, we can see.
Yeah. Okay, so I'm going to talk about using descriptors to design novel nanomaterials. I was told that I should give my talk at a quite general and elementary level. So I have done that. So for those of you who are specialists in the field, I apologize if the talk is at too elementary a level for you. So I'm, as you've been told, I'm from JNCSR in Bangalore, and I have the computational nanoscience group there. This is a picture of me with my students. So I'm going to tell you a little bit about how one designs novel materials using DFT. DFT is density functional theory, and how one might do that nowadays using high throughput searches, and how it is better to do that in coupled with using descriptors. So I'll tell you what are descriptors. I'll just talk about one project of ours where we did this for self-assembly. And I'll conclude by telling you a little bit about the current status of the field and concerns and outlook. So designing novel materials using density functional theory. So as you're probably aware, materials are so important that we use them to define human history and progress. So the progress of human civilizations is signaled by the materials that were used in that era, like you have the Stone Age, the Copper Age, the Bronze Age, the Iron Age, etc. And this cartoon, my students said people won't notice the joke here, which is that the Iron Age man is using an iron, and so this little laughing GIF was put in to draw your attention to the iron in the hand of the Iron Age man. So how many materials exist in nature? There are about 98 naturally occurring elements. The rest have been synthesized in the lab. And it is estimated that there are about 4,000 naturally occurring minerals. But we can increase the number of materials by making materials. So we can make new materials, which is what a lot of focus is of a material scientist today. So this is, of course, a periodic table made with Lego blocks to signal that if you're a material scientist today, then the periodic table is kind of your toy box, and using the elements of the periodic table as your building blocks, you can make lots of new materials. Now, this is not a new thing. Already, thousands of years ago, one of the first of these man-made materials was bronze. So I think this is quite remarkable because already thousands of years ago, human beings realized that they can make a new material, and bronze is an alloy of copper and tin, and it has superior properties with respect to its constituent elements. For example, it is harder than copper alone, and it has some of the superior properties that it has compared to elemental metals is, for example, it does not rust. And even in India, the Bronze Age was quite remarkable. For example, we all hear about the Harappan civilization, and maybe many of you studied in school about this statue, this little statuette of the dancing girl of Mohenjo-daro. And this statuette is made of bronze. There were lots of Bronze Age weapons made in India which have been discovered. And how many such materials can potentially exist? So nowadays, of course, you look on the web, but when I started out as a scientist, we used to consult these volumes called the Landolt-Bernstein series, and they used to have a list of all the alloys, etc., that had been synthesized so far, and they would fill shelves and shelves in a library. So now, considering 9,000 crystal structure prototypes and only stoichiometric compositions, it has been estimated that if you have 4 elemental constituents, then you have 3 times 10 raised to 11 potential compounds. And if you have 5 constituents, then it increases to 10 raised to 13. So this is obviously a huge, huge chemical phase space. So how does one search in this? How did they find, how thousands of years ago did they find alloys like bronze, for example, or all the materials that we use today? So most of these were either accidental discoveries, like, there was some trace element while they were working in the smithy or whatever, or by trial and error. So these are just 2 cartoons, not about material synthesis, but about another famous ancient discovery, which is the discovery of the wheel. The cartoon on the left is sort of trying to visualize that the wheel was discovered accidentally. And the cartoon on the right is saying, okay, you try lots of different shapes, and then finally you find that a round shape makes a good wheel. So these are, of course, jokes, but in analogy with that, you can see that if you're trying to make a new material, maybe you find it by accident, or you keep trying different compositions, and you finally find something that seems to have superior properties. So this trial and error and brute force are not terribly efficient ways to proceed. People made it more systematic by doing combinatorial approaches. But increasingly, people started using calculations in recent years. So with the advent of high-performance computing, you can do high-throughput searches. I'll tell you a little bit about that. And ideally, you would use a combination of experiment and theory. Now, an example of these kinds of brute force approaches to trying many things is there's the Haber-Bosch process for the synthesis of ammonia, for which you need a catalyst to get nitrogen from the air and hydrogen and combine them to produce ammonia. Many people believe that this is actually the most important scientific discovery of the last century. Of course, there are many other candidates one might come up with, but it has been persuasively argued that this is the most important discovery because the fertilizers that were produced through this process feed more than half of the world's population. And how did they find the catalyst for this process? Initially, they searched systematically through about 2,500 catalysts to see which one was the best. And by now, about 250,000 catalysts have been tested. But this is not a very satisfactory way of proceeding. So increasingly, one wants to replace this trial and error or brute force method by what people call rational materials design. So this requires a to and fro between theory and experiment. So if you're doing theory like I do, then what would you do when you do rational materials design? You would take three materials, say material A, material B, material C, and then you do computations on them. And then you analyze these computations, and then you get some insight into design principles. You understand why these materials have the properties that they do. And once you get this insight, then you could perhaps design a new material, which is the best possible material to have the optimal properties for your desired application. So why do we do computations at all? Why don't we just do experiments? So nowadays, especially with increases in computer power, it is often cheaper and quicker to do the calculation than to do the experiment. And of course, these calculations have to be very accurate if they are to replace experiment. So we have increasingly reached a stage where the calculations are indeed so accurate that they can often replace experiment. I put can work from home slightly as a joke, but it's true, especially nowadays when one has lockdowns due to coronavirus, etc. One is in kind of a privileged position if one is a computational scientist, because you can carry out quite a lot of your research from home. But importantly, with calculations, you can get a greater understanding because you can separate out different effects. For example, if you want to know what contribution comes from relativistic effects or what contribution comes from magnetism, in a calculation, you can switch off the relativistic effects. You can switch off the magnetism. You can't really do that in an experiment. You can also simulate conditions that can be very difficult to achieve in a lab. For example, if you want to know what happens if something is subjected to very high pressures, in the lab, you need very fancy equipment to do that. You need a diamond anvil cell or something like that. But in a calculation, it's not very hard to just subject your material to high pressures. And you can make predictions for experimentalists to verify. So what is the basic problem that you're trying to solve when you're trying to understand what properties a material will have? It's the quantum many-body problem. So your system consists of some number of nuclei and some number of electrons. And these interact via the Coulomb interaction. And so you may have, the system might be atoms, molecules, a condensed matter system. And we can write down the Hamiltonian for the system. So the basic system is the many-electron Schrödinger equation. If relativistic effects are very important, then maybe we will write down the Dirac equation instead. And the solutions must also be properly anti-symmetrized to satisfy the Pauli exclusion principle. Now, we can write down this equation, but we don't really know how to solve this because it's a many-body equation. So how does one approach this? There are two basic ways one deals with this in condensed matter physics. You can either do many-body theory, where you retain the many-body nature, but you use a model Hamiltonian, or you can do density functional theory, which is what I do, where you map the system onto a system of one-particle Schrödinger equations. This is an exact mapping in principle, but it's approximate in practice, and you solve this numerically. So this is our many-body Hamiltonian. You have the kinetic energy of the nuclei, the kinetic energy of the electrons, the potential energy between nuclei, the potential energy between the nuclei and the electrons, and the potential energy between the electrons. And we usually make the Born-Oppenheimer approximation, which I guess most of you know about, so that we can separate out the electronic Hamiltonian. So the electronic Hamiltonian has the kinetic energy, the potential energy between the nuclei and the electrons, and the potential energy between the electrons. And it's this electron-electron interaction, the last term, which makes it a many-body problem that makes it a hard way to solve. And DFT is a way of including these troublesome electron-electron interactions. So I'm not going to tell you the theorems and the proof, etc., but I'll try to give you a feeling for it by making an analogy. So you map the many electron problem onto an equivalent one electron problem. So this might seem like a silly analogy to you, but I think it gives you a flavor for what it is. So it's as if you have a lot of people with complicated interactions between them. They may love each other, dislike each other, hate each other, etc.
Shobhana, can I interrupt
Yeah.
for a second? Somebody
Yeah.
is saying that you should click on that hide below so that it's obstructing some of your slides. That there is a.
Okay. Yeah.
Can
Okay.
you click on hide?
Yeah. Done. Okay. So so it's as if the blue men on this are the nuclei, and the red women are the electrons. And the problem we want to solve is we want to arrange all these people in such a way that we have achieved a globally maximal level of happiness, which is obviously a very complicated problem to solve. And in DFT, what you do is you instead replace this by a problem where you instead have just one woman whom you have to move to achieve the maximal level of happiness. And this is obviously a much simpler problem to solve. Now, when you do this, you do increase some complexity in the problem, which is you introduce an extra term in your Hamiltonian, which is called the exchange correlation potential, which I have schematically shown by putting a face mask on the men to say that there's an extra term in the Hamiltonian. Though I should say that for correctness, the exchange correlation interaction is not between nuclei or between nuclei and electrons. It's actually between electrons and electrons. But anyway, there's an extra term. And the problem you have is that okay, so before I go into that, let me say that the DFT was invented by Walter Cole, who has a very interesting personal history because as a young boy, he grew up in Austria, and he was shipped out from Austria to England as a young boy to escape the Nazis on what were called Kindertransport. These were groups of young children who were sent to England to escape the Nazis. And his parents were then killed in a concentration camp. And then when he was in England, when the war broke out, because he was of Austrian origin, he was considered an enemy alien, and then he was imprisoned in a prison camp in Canada. So it was not an easy childhood. But in this prison camp, he was taught physics and mathematics by an older prisoner, and that's what got him interested in physics. And for his discovery of DFT, he was given the Nobel Prize in 1998. DFT is extremely successful. There are tens of thousands of papers, tens and thousands of citations. So if you look in the PhysRev journals and you look at the 10 most cited papers all of them, which I've listed here, are related to DFT. So there is one big unsolved problem in DFT, which is this exchange correlation potential, which I represented schematically by the face mask. We still don't know what is this exact form of this exchange correlation potential. That is, we don't know what is this exact design of a face mask such that the solution to the one particle problem is exactly the same as the solution to the many body problem. We know that it exists, but we don't know what it is. But we have some very good guesses, which is why we are able to proceed to do calculations using DFT. So DFT calculations are often also called first principles calculations or ab initio calculations, because the only input that you feed in is atomic numbers and atomic masses, and then your output are total energies, densities, etc. So how we use density functional theory is that we input a structure and a composition, we do DFT computations, and our output is mostly very accurate results for total energy and properties of a system. So as I said, nowadays people often use them to do high throughput searches. That is, you automate the procedure so that you can do thousands and thousands of computations on materials. So for example, here is a calculation that was done to see if you can get binary alloys of two metals. So on the x-axis and the y-axis are lots of metals listed. And the color tells you what is the mixing tendency, that is, what is the heat of formation of the binary alloy that you make out of these two. Okay, and so these colors are all from the DFT calculation. And then in this triangle, it tells you what is the degree of agreement between experiment and theory. So a green circle means that both the calculation and the experiment agree that the alloy forms. A gray circle means that both the experiment and calculation agree that the alloy does not form. So for most of the combinations, you see that you have agreement with experiment and theory. But in some cases, we see that there is a disagreement. So it tells you that DFT calculations are mostly accurate, but not always accurate. Now, how can we use these kinds of high throughput calculations? This is another rather famous example of high throughput calculations. So as you may know, nowadays the perovskites of the form AbO3 have been attracting a lot of attention for applications in solar cells, for LEDs, for water splitting, etc. So this was one such calculation where they looked at 2,601 possible perovskites. So basically all possible perovskites, where they looked at A, B, O3, they looked at all possible metals for A, all possible metals for B. And they looked at two things with the calculation. They looked at the heat of formation, that is, they looked at whether the perovskite forms or not. And they looked at the band gap, because this was for solar water splitting. So you need the band gap to be in a certain range. And you also need the band alignment to be in a certain position, the valence band edge and the conduction band edge, with respect to the oxygen evolution and hydrogen evolution reactions, for it to be suitable for water splitting. And they found that out of these 2,601 combinations, 10 possibilities might be suitable. So then as an experimentalist, you can focus on only these 10 and try to synthesize them. So that is the idea behind this kind of calculation. But if you have this kind of large database, the other thing you can do is you can try to come up with descriptors. So what are descriptors? Descriptors are some combination of microscopic properties of the system that correlate well with the macroscopic property of interest. So to be useful, they should be quick and easy to compute, yet be accurate, and they can be used to design materials with desired properties. So what am I saying here? I'm saying that if it's very hard, it still takes a lot. I mean, computers are quick now, and DFT calculations are certainly quicker than they used to be, but it still takes a lot of time to search through 2,601 compositions or whatever. So you would like to have some way to quickly decide to screen a lot of materials and guess whether they might be a good candidate that you can then go on to do DFT calculations on, or you can then do experiments on. So this is what a descriptor is. So the idea nowadays is that you may do first an experiment and DFT calculations. You make a DFT database. You analyze it to get descriptors. So these descriptors you could do just by using your brain or your chemical intuition or whatever. Or increasingly, people are getting them with machine learning. And then once you have these descriptors, you make some predictions using these descriptors, and then you verify whether these descriptors work or not. So it has been said in this review article on descriptors that the descriptor is the language which the researcher speaks to the database. So what is a descriptor? A descriptor is basically something that indicates correlation. And if you've identified a good descriptor, you should see a clustering of properties in descriptor space. The descriptor itself need not be an observable, but the important thing about a descriptor is it should have predictive power, which is what makes it useful. So here I was talking to my students and saying, can you think about something I can cite as an example of a descriptor? And one of my students told me about this paper where somebody did this research. It's a serious paper in the sense that it was published in a serious journal, the New England Journal of Medicine, which, as you may know, is one of the top journals in biology and medical research. And it showed that there's a very strong correlation between the number of Nobel laureates that a population has and the chocolate consumption in that country. Okay, so this is plotted here. There are some outliers like Sweden, etc., and Germany, but in general, you have a good correlation. Now, you may think this is stupid, but there may be a reason for this underlying correlation as well, which may not be obvious when you just look at the descriptor. In this case, probably the reason for this correlation is countries which are rich, have money to spend on scientific research, and they also have people who are rich enough to spend a lot of money on non-essential like chocolate. So there may be reasons that are hidden from us, not immediately obvious, but which explain why you get these correlations. Of course, sometimes the correlations might be completely stupid and accidental. So I was looking at a search on the web and I found, for example, that you get these bizarre correlations, like you see in the US, the age of Miss America in a year and the number of murders by steam in a year. Okay, now I don't even know that there were any murders by steam, but apparently there are. And if you plot the two, you see the two seem to track each other. So of course, you can also end up with these accidental correlations, and then you have to obviously test if they work or not. And so what is the descriptor doing? So there is this story, there's this joke you might have heard about, that there's this drunk guy and he's lost his car keys and he's looking under a lamppost for his car keys. And a policeman comes along and says, "What are you doing?" And he says, "I've lost my car keys." And he says, "Are you sure you lost them here?" And he says, "No, but it's much easier to look under the lamppost." So what the descriptor does is it's basically shining a light in a certain area of your face space. It's telling you, look here, you're most likely to find what you want if you look here. That's what the descriptor does. So how do you formulate these descriptors? You can formulate them by physical or chemical intuition. You can get them by numerical regression techniques, or as I said, increasingly you get them by machine learning. Now, we are actually familiar with descriptors, though we may not be calling them that. So I don't know how many of you will recognize what this is. This is, okay, maybe the year is wrong here by a couple of years, but this, as you may recognize, is an early version of the periodic table, which was developed by Mendeleev. And this was developed by physical or chemical intuition. And when Mendeleev developed it, basically this periodic table was just finding correlations, finding a way of arranging the elements so that the rows and the columns were descriptors. Okay? Because at that time, it was not known what the rows and the columns meant. Okay? So only much later came the discovery of the electron, then the Rutherford model of the atom, then the Bohr model of the atom. And now we know that the rows and the columns tell us something about the number of electronic shells and the number of valence electrons. But at that point, nobody knew what the descriptors meant. It was just a way of arranging things so that you had these two descriptors, which were the rows and the columns, and you had a clustering of columns of properties in this descriptor space, okay, which of course you all know about the periodic table. And it also had predictive power because, for example, these elements, which I had circled, were not initially known. They were discovered after the periodic table was made, but one could predict not only that they existed, but one could predict what properties they might have based on the fact of their position in this descriptor space. So now let me talk a little bit about structure, predicting structure. So structure is one of the properties that we really want to predict because structure-property relationships lie at the heart of materials science. And the first step in any first principles calculation is to input the structure. But predicting the structure from first principles with no knowledge apart from the chemical composition is really hard. So in fact, in this rather famous article which John Maddox, who was the editor of Nature, wrote in 1988, he had this sentence. He said, one of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. Now, this sentence was written in 1988, and of course, we've made considerable progress since then, but it is still largely true, I would say, this sentence. Okay, so for example, let's look at the elements. Let's look at the metals. Here are the elements arranged according to the periodic table, and the shapes here say the colors and the hexagon squares, etc., not hexagons, pentagons, circles, squares, etc., tell you what structure those metals have in their three-dimensional bulk form. And there seems to be some clustering, but it's still a bit random. Okay, there's no obvious pattern to it. There's no obvious descriptor for why a certain metal has a certain structure. And if you're just given the atomic number, it is very hard to predict with no further information what crystal structure it will form. So right now, if we're doing a DFT calculation, what do? We do sort of the brute force approach, which is, for example, okay, this is not a metal. This is an example I took for silicon, but it's the same for metal also. You just think of all possible structures it might have. So you do a DFT calculation, energy versus lattice constant. You try the diamond structure, the beta tin structure, the HCP structure, the FCC structure, the BCC structure, etc. And then you see which one gives you the lowest total energy, and you say that is probably the structure. But there's an infinite number of structures you could try. So you can never have the confidence that you've actually found the global minimum structure. And how do you know which structures to try out? So this is really a hard problem. So another famous problem in structural prediction, which people often use as a sort of canonical problem, is what they call predicting the structure of the octet compounds. These are compounds formed of two elements where the sum of the valencies adds up to 8. Okay, so like, sodium chloride, magnesium oxide, etc. So most commonly, these octet compounds form in the rock salt structure or the zinc blende structure or the wurtzite structure. But there seems to be no pattern, no easy descriptor that explains which of these compounds a given pair of elements will take as its lowest energy structure. So a long time ago, sort of at the end of the 60s, early 70s, Van Vechten and Phillips, they came up with a pair of descriptors. Okay, they said that if you plot what is called the heteropolar energy gap and the homopolar energy gap of the compounds on the two axes, then they seem to separate out into two groups, which will have two different structures. But the thing is, you still have to do the calculation or the experiment to know these gaps, because these gaps depend on the dielectric constant and the lattice constant of the crystal. And so you have to do the structural calculation to calculate the dielectric constant, to calculate the lattice constant. So you cannot predict it on knowledge of the elemental constituents alone. You have to know something about the compound to predict what structure the compound will have. So that's not very satisfactory intellectually. You would like to know something about just sodium and just chlorine to predict what structure sodium chloride would have. So there is someone called Pettifer, who in 1984, he came up with something called the chemical scale for all the elements. Okay, so that chemical scale is a number. It's something like electronegativity or something, which is just defined for all the elements. This is plotted in the left-hand graph. And if you plot the chemical scale for A and the chemical scale for B of all the octet compounds, then you seem to get a phase diagram where the different structures separate out in this phase space. But again, we don't understand why. And he just came up with this chemical scale by inspection. So it's a brilliant discovery, but it's not something that you know how to then extend for something else. So now I'll tell you a little bit about work that we did in my group, where we tried to get descriptors again for structure. So here, the question we asked, in analogy with what was asked for the octet compounds, is, so if you have organic molecules, they can self-assemble into different geometries. So the question we asked is, if you have just the formula and structure of, say, two isolated molecules, can we predict what will be the geometry of the self-assembled structures that they will form? So here is this yellow molecule, and here is this lilac molecule. And I know something just about the yellow molecule, and I know something just about the lilac molecule. And can I predict what structure I will get when I bring the yellow and the lilac molecules together? So this was the aim of our project, which we did together with the experimental group of George Thomas from IIT Guwahati. So to do this, we have what is called small data. So this is sort of interesting. Why do I say small data? Because usually when people developed descriptors in the past, when they did a descriptor kind of approach to a problem, they work with what they call big data. But we decided to work with small data. So we have 3 host molecules, which I've shown here. We call them P4A, P4B, P3A. Now, these are all what are called phenylene ethylenes. And they're all sort of similar in that they have a long molecule and they have head groups at the end. And they're similar, but they're also different, and those differences are important. So 2 of these have long backbones. One of them has a shorter backbone. 2 of them have COOH groups at both ends, at the terminal groups. This one has at only one end. It has the COH groups. So they are similar, they're clearly related, but they're different. And the guest molecules are naphthalene, phenanthrene, etc. And one can look at them the reason I drew them as these sort of pie-shaped wedges is that you can look upon them as angular fragments of coronine, which is this molecule here. Now, let's look just at the host molecules first. When you put these host molecules, when you deposit them on a graphene or graphite substrate, there are 2 different ways where, in principle, they can self-assemble. And they self-assemble by forming hydrogen bonds, which are these red dashed lines. And it can form this way, which is called the linear arrangement, and this way, which is called the hex arrangement. So let me just show you them. So the first one on the left is a lin arrangement. So you see how the molecules are arranging, and here the second one is the hex arrangement. Now, when they form these arrangements, there are either small cavities or big cavities, which are shown by these magenta things. And there are guest molecules that can go and sit in these cavities. And the question I'm asking is, can I predict the relative energetics of the 2 patterns by looking at just the isolated host molecules? So we've done standard DFT calculations using Siesta. And to compare, because we have different numbers, densities of host and guest molecules, we look at the Gibbs free energy. So why did we choose these 3 molecules? These host molecules. It's very interesting because both our calculations and STM experiments show that these 3 host molecules, I told you, they're similar but different. And these differences are enough that they form different patterns. So if you put P4A, it forms the hex. If you put P4B, it forms the lin. And if you put P3A, it forms neither the hex nor the lin. It doesn't form an ordered pattern. It forms a glass-like pattern, which is disordered. Okay? And we can, the advantage of DFT is you can do a calculation not just on the lowest energy structure, but also on the other structure. So we can find the energy difference between the hex and the lin. So if we do that, if you get a negative number, these numbers in red, that means the hex is favored. If you get a positive number, it means the lin is favored. And if the energy difference between the 2 is small, then you have a competition between these 2 structures, which is why the glass forms. Now, what happens if you introduce guest molecules? Now, in some cases, for example, for P4A, if you introduce the guest molecule, the pattern looks very similar, except where you have a cavity here, the guest molecule goes and sits here. So nothing much happens. But what's interesting is in some cases, you have a structural phase transition when you introduce the guest. So for example, for P4B, if you have just the host, you have the lin pattern. And here, when you introduce the guest, it becomes the hex pattern. So this is what happens. Here is the summary of what happens. You can have, for P4A, no matter what the guest is, you always have hex. For P3A, you have glass, then hex, 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 hex. And for P4B, you have lin, then hex, hex, hex. And you can do it with DFT also, and DFT agrees always with the experiment about whether you have the hex or the glass or the lin. And we can also, with DFT, you get charge densities, and you can look at the charge density differences when you form bonds between the hex and between the host and the guest. And these alternating lines of red and blue loads are signatures of hydrogen bonds being formed. So you can see that hydrogen bonds form between the host and the guest, which is what stabilizes these arrangements. And you can calculate the energy by which the whole system is lowered versus the number of these bonds formed, and then you can get the energy per hydrogen bond. Now comes this descriptor stuff, which is the part that's kind of weird and non-standard. So we wanted to see if we can find some way to find a descriptor for the energy of this host network. And since the three hosts differed in the number of COH groups they had, and the length of the molecule, and the number of these alkoxy side chains, we wanted some formula that involves these quantities. And the brilliance of my student Sukanya Ghosh was that she got a feeling from her calculations and by looking at the data what form they should have. So it has number of COH groups times the length of the molecule times some unknown power alpha, and 1 plus the number of side chains times some unknown power beta. So we don't know this alpha and beta yet. And then by doing a linear regression and looking from DFT, we know the difference in energy between the hex and the lin. And then this host descriptor, which has this form, she found that this power alpha is 1 and this power beta is 1/8. Okay, so I agree this is weird, and right now it looks like numerology, and you think, what the hell have you achieved with this? What is the point of this? What do we gain? The surprising thing is that this has a lot of predictive power, because now we can look at other molecules that were not part of our training set to get the descriptor. So here are these, for example, 4 other molecules. And this one has no side chains. This one also has no side chains. This one has no head groups and is much longer, etc. So for these molecules, we can calculate this formula. It just takes, 5 seconds to calculate this formula for each of these molecules. And by evaluating the value of this host descriptor, you see where it falls on this line. And by seeing where these purple stars fall on this line, you can predict that this molecule will form the hex, this molecule will form a glass, and these 2 molecules will form the lid. And now you do the experiment, and indeed all these predictions turn out to be right. Okay? And you can do even better than that, because you can also do the DFT calculation on these systems. And you can actually get the value of the difference in energy between the hex and lin between these. And those are these yellow squares. And you see they do really pretty well. So this descriptor approach is very useful because it allows you to predict the structure and predict not just the structure, but it allows you to predict the energy difference between competing structures. And what if we didn't do it? I mean, what if we had the wrong descriptor? Like supposing we didn't have this alkoxy side chain at all. Then if you can still find a descriptor, but then your predictions are totally wrong. you get the energy difference is completely wrong, and you get the structure also completely wrong. I mean, one of them comes out right, but two of them come out wrong. Okay, now what about the guest molecules? For the guest molecules, the descriptor we get is done a little bit differently. So it's a geometric descriptor. So you take the polygon formed by the hydrogen atoms on the periphery of each guest molecule. You draw a circle that passes through as many vertices of this polygon as possible. And you count how many hydrogen atoms fall on the circle. And that number is the guest descriptor. Okay, so this descriptor was sort of not developed using a regression procedure. It was developed from sort of physical and chemical intuition. And then if you plot the host descriptor and the guest descriptor, and you see where the molecules fall, the host guest pairs fall, you have 18 pairs. And then you color them according to the difference between the host and the guest, the lin and the hex, as obtained from DFT. That's what the colors of these circles are. You see that you get a very nice phase diagram in descriptor space. So you have a clustering of structures in descriptor space. So you go from strongly lin here to strongly hex here. And for any other related structures, you just have to calculate the host descriptor and the guest descriptor. And from this phase diagram, you can predict what structure they will have. Okay, so that's the advantage of having identified these descriptors. What is the physical interpretation? Okay, so now I have to tell you that though I was very happy with this project because it was some slightly crazy idea we had that we will try to find descriptors, I was also rather disturbed by it. The guest descriptor, I can partly identify a physical interpretation, in that for the hex structures, the guest descriptor is equal to the number of hydrogen bonds that you form. But in the lin structures, it's not even clear what that is, because for something like this, I'm not even sure I can actually calculate the number of hydrogen bonds. It's very hard to decide where you have a hydrogen bond, where you don't have a hydrogen bond. And it's kind of surprising that this descriptor works. But for the host descriptor, I actually have no interpretation. Okay, so I don't understand what that 1/8 power for the number of alkoxy side chains means, for example. I don't understand it at all. So now, I mean, it's possible that some point in the future we will understand it, okay? Because, for example, if you look at the periodic table, when Mendeleev first came up with those rows and the columns of the periodic table, people didn't know what the rows and the columns meant. Okay, it was just a way of arranging things and coming up with these descriptors, and only much later when you came up with the structure of the atom did you know what the rows and the columns meant. I'm not saying that I found something like the periodic table, but it may mean that at some point in the future you will know what this form of the descriptor meant, but I do not yet know what it is. And it does bother me because I'm trained as a theoretical physicist, and I'm used to deriving formulae for which I can give a physical interpretation to each term in the formula. I'm not used to having a formula where I don't know what something means. So this seems to be true in general for the kinds of descriptors we are getting these days. For example, a lot of people are obtaining descriptors using machine learning nowadays. So if we go back to this problem that I told you about of the structure of the binary octet compounds, so this is a very well-known paper. It was done by Luca Giringelli and co-workers and Matthias Scheffler. So they took their data for the energetics of a vast number of octet compounds, and they did a machine learning study out of it. And they found that they get a nice two descriptors for it. So if you have an octet compound formed out of two elements A and B, the two descriptors for which they get a nice separation in descriptor space is these. I said nice descriptors in that you get a good separation of energetics, etc. But the descriptors themselves, the first one is the radius of the s orbital of A minus the p orbital of B times the exponential of minus the s orbital of A. And the other descriptor is the ionization potential of B minus the electron affinity of B divided by the radius of the p orbital of A squared. Now, again, this is a very intellectually unsatisfactory form, because this is something for which we can't immediately assign a physical interpretation. We can say it works, we can say you can make predictions, but we don't really have a nice physical interpretation, chemical interpretation of what this means. So you can also get electronic properties from machine learning. For example, here is a study that was done a few years ago, where people just tried to see if you can predict from just structure and energetics, can you predict whether something would be an insulator or a metal? And they got some kind of separation in a descriptor space. What was the two descriptors they got? One was the ratio between the fusion enthalpy and thermal conductivity, and the other was the average molar volume. Okay, but again, this to me is not very satisfactory, because the thermal conductivity, I mean, this may have some physical meaning. It's known that thermal conductivity will be related to electronic properties, but I mean, to calculate the thermal conductivity is a lot harder than just seeing whether something is an insulator or a metal. So it's not clear that it's very useful. Okay, so I just want to end by making some general comments, I mean, about what's happening. As you all know right now in condensed matter physics, as in most fields of physics, machine learning is very popular. I'm watching these developments with great interest. I'm also sort of tentatively getting into it, but I do find it a little bit disturbing. Maybe it's just a new paradigm, a new way of doing science, but it does bother me, because what's coming out, though it's interesting, it's certainly very different from what we've been used to. So this was an article that came in the New York Times. It said, as machine learning becomes more powerful, the field's researchers increasingly find themselves unable to account for what their algorithms know or how they know it. And that article had this thing, it said this isn't merely a theoretical concern. In 2018, the European Union will begin enforcing a law requiring that any decision made by a machine should be readily explainable. Okay, and certainly in physics, what we're getting out of machine learning does not seem to be readily explainable. So I'm pretty much done. So I'm saying that descriptors are certainly seeming to be very useful, and it's using a descriptor-based approach to materials design seems to be very useful. People are using it for lots of things. People are using it to design catalysts, to design thermoelectrics, to design water splitting materials, photovoltaics, etc. But what we have to figure out is how to combine intuition with numerical and computational techniques. We have to decide, so the decisions you have to make is how to define the parameter space. It's interesting to decide how big should the database be. And what perhaps we have to grapple with most is machine learning going to provide the silver bullet, and is it really going to give us information that will satisfy us at an intellectual level, or will it just be useful but leave us baffled about why this works? So thank you very much, and I'm done. Thank you.
So thank you, Professor Narasimhan, for such an interesting talk. It was very nice description. So now it's open for time. Now it's open for questions.
Yeah, can I ask a question to begin with? Girish
Yeah.
Saglur?
Yeah.
So thanks, Shobhanaji, for an excellent talk. And there are a lot of things I learned, which I, of course, I mean, I'm the last person to say that I should know all these things, but I actually didn't know most of these things. And thanks for enlightening us. But I just have few questions and comments. Uh, I sometimes get the feeling that the reason why I remember one of your slides said quoted some scientist who said it's a tragedy that we cannot predict the structure of solids based on the stoichiometry even today. I
Yeah.
I feel that that is for two reasons. One is, of course, the scientific reason that maybe this all these length scales and energy scales all get mixed up in a way that we can't easily separate. So I think condensed matter physicists have kind of, I feel, been misled by Anderson with his more is different philosophy, and they have taken it so literally and kind of got brainwashed by it that they have simply failed to explore other paradigms. So as a result, that aspect of condensed matter physics is kind of been completely neglected, and the main reason I feel is Anderson. What do you feel about that?
Well, that's kind of a philosophical question, but I don't think it's really a question of lens scales being mixed up. Why are you comparing? I mean, why is combining Anderson's more is different with respect with lens scales being mixed up? I mean, the two are
But
not
more may not
necessarily
be
the
different.
same thing. The
No,
two
what
are
I'm trying to
different
say,
things,
more may
right?
not be different. More may not be different. In fact, we already know that there is a fundamental law of nature, which is basically electrodynamics and quantum mechanics should explain all of solid state physics. The you know the his claim that at various scales you need different ad hoc approaches, I feel has done a disservice to the subject. That's what I feel. What do you feel? You feel that's still okay?
No, I don't think. I mean, for example, if you're doing density functional theory, I don't think you're uh, using any Andersonian paradigm or anything like that. And the problem is that, I mean, as you're saying, you know the fundamental interactions, you know the Hamiltonian, but it's a many body problem, so we don't know how to solve it. But that is not still the problem of structure prediction. The problem of structure prediction is something different. That that you have too many degrees of freedom, and we don't know what it is that makes something. I mean, it's a question of having an energy landscape with multiple minima, and you don't even know what the energy landscape is.
Yeah, I agree with that. But anyway, we'll discuss that later. So the other comment relates to these descriptors themselves. So yeah, you have mentioned. I mean, you pointed out several times that they tend to be ad hoc. Uh, so that's exactly my concern also, that there is no end to how many such ad hoc characterizations that you can come up with. In fact, my student and I, we started off that way. We wanted to classify superconductors based on machine learning, but then we ended up with this chicken and egg problem. That there you need lot of for machine learning you need lot of data, but then if you all, where does that data come from? It either comes from experiment or it comes from simulation. But if you can do experiments that much of an extent, or you can do simulation that much of an extent, then you don't need machine learning. So it's like a chicken and egg problem.
No, I don't. I don't agree with that. The whole point is that you still can make predictions about things which aren't in your database, I would say. Uh, so in two ways. One is that it could help you look for compositions of materials that are not there in your original database. Or if you find a correlation between properties, then you might, for example, be able to say that a material that has this kind of property will also have that kind of property. So I don't think it's a chicken and egg thing. I think it actually helps you look for something that you don't already have. And what we found from our calculation, I don't know if we were lucky or it's a signal of something more fundamental. We actually started with a very small database and we were able to make predictions about things that weren't in our database. But what bothers me is not a chicken and egg thing. What bothers me is whether we are getting fundamental insights or whether we are only getting something useful.
Yeah, and also the parameter space is so limited, so that meaning, like, see, any interpolation will be good even if it is fundamentally wrong. So if you restrict your parameter space sufficiently, so in that sense, I think many of these approaches probably are not giving you fundamental insight. They are merely interpolating to some crude extent. Okay, so do you feel
Well,
that? Do you,
well, first of all, I think it's still a question of how to define the parameter space because in principle there are other things you can look upon in the parameter space. You still have to identify which parameters to focus on. And of course, in some sense, you are interpolating, but how to interpolate is still important. And that is why you need the machine learning. And if it is useful, I think it is still very important.
okay. Anyway, thanks for your response. So, please, other people can please ask.
Is there anybody else who has a question?
So, just to break the silence, I have one comment about this wheel thing. So, you remember in the beginning, you showed us a slide about the wheel having been invented by accident. In fact, I read some time back about why biologists were speculating why organisms didn't evolve wheel-like structures, why they only evolved leg-like structures. Uh, so the speculation was that in order for wheels to evolve, you need a flat surface that the wheel can roll on.
Uh-huh.
And most of the flat surfaces are usually artificial. But then, but your slides seem. I mean, not only your slides, but we know that wheels were invented by prehistoric humans who probably did that before they invented roads. So I think that argument doesn't seem to be that convincing now. And now that I think about it, because actually the wheel came before the road. So that if that is true, then animals and should have evolved wheel-like structures instead of legs, which would have been far more efficient.
Yeah, so I'm trying to remember. I know I read a novel where there's this symbiotic relationship between the organisms and these seed pods, which they use as wheels to move, but I've forgotten what novel it is. I remember the story, but I've forgotten the novel. Anyway, this is totally orthogonal to the
Yeah, of
talk.
course. Right. But it's related to your slide.
Is somebody conducting the seminar? Should I stop? Should I wait? What should I do?
Yeah,
So,
so
ma'am,
student, yeah, Ujjwal, Sakya,
yeah,
go ahead.
ma'am, can I ask a question?
Yes,
Yeah,
of course.
please.
So, ma'am, first of all, thank you for this wonderful talk. It was really informative, especially for me. So, and right now I am actually doing something in this area. So, like, and now I'm trying to find a descriptor for vacancy formation energy in 2D materials.
Mhm.
So, so, ma'am, actually, as you explained, there are some machine learning techniques or like numerical regression or physical chemical approaches uh, to first predict this descriptor.
Mhm.
So, my the thing is, suppose first I did some calculation, I get some result, then at that stage I I have to find a descriptor. So then what should I keep in mind at that point to cause this descriptor? I don't know how easy it will be. For example, in one of your case, it was the number of hydrogen fallen in the circle,
Yeah.
and that other case, it was really complicated formula, and like. For doing the brainstorming, it should be in the right direction. So, what should I keep in mind whenever I try to find a descriptor? So,
I
any
mean,
advice?
that's a really hard question, I mean, because that's the heart of the whole thing, right? And
Yeah, ma'am.
it will change from problem to problem.
Yeah,
But
definitely.
what I can say is that what I haven't shown you is that we did a lot of model calculations to get an idea what is the important parameters.
Mm-mm.
Like we tried varying different things. With the same systems, we tried to vary the distances, um, vary the number of molecules, etc. Trying to get a feeling for whether, for example, uh, the the length of the side chains, if you notice, didn't come in our formula. And we tried
Mm-mm.
to get a feeling for whether that is important because there are lots of different kinds of hydrogen bonds that are formed in these networks. And we tried to get an estimate of the different energies of these different hydrogen bonds to get a feeling for which hydrogen bonds were dominating the energetics.
Okay.
And so, for example, for the host guest, I realized it was these hydrogen bonds that were dominating it. And then I looked at it and I said, okay, so it is, if I look at it geometrically, this is a feeling. But I can't, at some level, it is a sudden moment of inspiration also,
Yeah,
which is
ma'am.
very hard to describe in words. Like, like for Sukanya, for example, my student, at some point she was saying, "Oh, I should have this formula." She had something in the numerator, and she realized it would blow up if she had no hedge groups,
Mm.
and so she put it in the denominator because it would decrease. And then if she didn't have that 1 plus, it would become an infinite thing. So she put that 1 plus, etc.
Okay.
So it's hard to say. It's hard to generalize this to another problem, you know.
So ma'am, basically we have to work through that part and see what's around us, like that.
Yeah, I mean, of course, you can also just blindly use some machine learning algorithm. But if I look at the papers in the literature where they've done this, it seems to me that they have used a certain amount of physical or chemical intuition about which parameters to keep, which ones to discard before they do the regression or the machine learning or whatever.
Okay. So, ma'am, one more question. So, another thing I found very interesting that you use that small data, like you specify it. So, because sometimes it's very difficult to get a big, large data set.
Yeah.
So, what's your feeling like? Is it like small data set is sufficient enough to accurately predict these descriptors, or
This is something I don't know the answer to, in the sense that I would generally have thought you need a big data set to get a descriptor, and that is the general feeling in the field. And I don't know if we were just incredibly lucky that we got something that worked so well with a small data set, or whether there's something fundamentally different in the nature of the problem that we were looking at that small data sufficed. And I really do not know that. I mean, this is certainly something I want to understand, but I don't understand yet. I mean, by looking at small data, I think I was able to get some physical intuition, which I may not be able to get if I had to look at thousands of cases. Because if I look at 3 cases or 15 cases or something, I at least am able to develop more physical intuition. But I don't think it is always guaranteed that you will be able to succeed with small data. So I do not know the answer to that.
Thank you, ma'am.
So any other question? Yeah, if not,
Yeah, okay. No, I just read a news item just recently that European Union is thinking of bringing in a law which penalizes these big companies like Google and these things. So until if they use machine learning to do certain, I mean, if they develop commercial products using machine learning, unless it is explainable, they're going to be heavily fined. Apparently, EU is.
Well, that was the last slide I showed.
Oh,
right?
you did. Okay, you yourself did that. Okay, fine. No, I also saw it somewhere else. Yeah, that's really alarming, isn't it? Because that's not going to work. Because that will really put brakes on the subject quite a lot.
Yeah, but I also understand their concerns. For example, people tell me, I mean, the kind of places where machine learning can not work is, okay, to go back to another interest of mine. So, for example, if you use a machine learning algorithm to screen CVs for people who are applying for jobs, okay, then apparently they found that a lot of these machine learning algorithms were eliminating women from applying for jobs, just because if you look at the correlation with the successful people who already had jobs, then most of them were men. And so the algorithm just assumes that, okay, so if you're a woman, you won't get it. It's not an explicit bias, it's just finding that correlation, and so therefore saying, okay, so if you're a woman, you shouldn't get the job. But that is embedded somewhere deep within. So you don't realize it, and so at some point it just finds the correlation that the people who are getting jobs, who have got jobs in the past, are men, and so it eliminates the women's CVs. So that's the kind of concern people have about using machine learning in some automatized way to make decisions.
So if there are no further questions, let's thank Professor Shobna Narasimhan for really giving very interesting talk, and hope sometimes he would visit us in the department. And
I would love to. Thank you.
Yeah, I think the time is due. Yeah. Once this Corona thing goes away, we should invite her.
Yeah, or
And
we
I
can
have
go
to
to
say,
Bangalore.
I've had excellent students from your department as well, whom I've been very happy to have worked with me.
Okay, that's great to know. Yeah.
so
All right.
with this, yeah, Professor Ghosh.
Yeah. Thanks, Shobna. So
Thank you very much.
we'll be in touch.
So thank you very much, everyone, and thank you, Shobna ma'am. And with this, we conclude the colloquium and say goodbye, all of you.
Okay. Bye.